Morning, everyone. So yesterday we started into types of organic reactions. We started off with the family of alkanes because based on their really high bond enthalpies and based on them not being polar, they are fairly unreactive. We're going to find as we step through the next couple of days here and learn other styles of reactions, it'll be a really good way to actually keep your reactions clear by drawing a mind map. So I'd encourage you to sort of each day as we just start learning more reactions, as the mind map gets a little bit more intensive, we can just practice that there, and that way you'll remember the reaction conditions that you'll need. So far, our mind map here is actually fairly simple. We'll do this for a warm up here. We start off here with just our alkane family. So we know that they're saturated, CN 2N plus 2. So far, we've seen alkanes perform two different types of reactions. In the presence of oxygen, it can undergo a combustion reaction. If it wasn't a substitute alkane here, we definitely form the CO2s, carbons, and carbon monoxides here. I'm just going to say CP for short. CP actually stands for combustion products, and temporarily you can just make a list for yourself here. The combustion products we would have assumed, if it was complete combustion, we would assume to get fully CO2 and water. If it was incomplete combustion, if I didn't have enough oxygen present, instead of the carbon fully oxidized, we're going to end up forming carbon as solid. It forms a dirtier flame, and carbon monoxide is a gas, which is a toxic colorless gas. Okay. So far, alkanes, they burn. In fact, burning reaction is going to be very common for all organic chemicals. Today, we're going to focus most on alkenes. Alkenes can also, in the presence of oxygen, end up forming these combustion products as well. Alkanes do one more interesting type of reaction here. This one here, the reactants that are needed are either Cl2 or Br2. But this one needed a reaction condition. We needed that high energy light source, UV, to actually cause the substitution reaction. It was a free radical chain mechanism here. And basically, instead of being just a fully hydrocarbon, just C's and H's, we end up substituting in some Cl's and some Brs. There's two different names we can give to these ones here. Because Cl2 and Br2 are halogens, you can call these halogenoalkanes. So they're alkanes with halogens. Or you can also refer to them as alkyl halides. This is sort of getting back into a little bit of IUPAC naming here. You can think of the family as an alkane, and it's just halogen substituted. Or you can think of it, no, it's a halide. It's a compound that has a halogen inside, and we just have branches that are branched off that halogen. So both ways are fine. Today, as we start looking at alkene reactions, we're going to build to this mind map. And it's a good way, just take 5-10 minutes or so, just every day as you learn more reactions, just slowly draw the mind map for yourself as well. Just to practice this free radical chain mechanism here, I want you to, can you show the radical chain mechanism for the following reaction here? Let's do it with bromine this time. Bromine is a little bit safer to work with than chlorine gas. Bromine is also a liquid. It's also like a red-brown kind of color here. Let's react it here with ethane. All right. So they're going to ask you to sort of dig through here a little bit. So radical, we know this one here has an unpaired electron. Notice unpaired electron doesn't necessarily mean charge, but it is very, very reactive. So very reactive. I don't like having an odd number of electrons. I'm going to do whatever I can to bond that electron there. Okay. So the conclusion is actually fairly simple. Well, this is a substitution reaction. So instead of just an ethane that has all C's and H's, what if I start substituting in the Br? I'm going to end up getting maybe, yeah, the CH3, CH2, most of them are still there, but maybe one of the places now has a bromine, or two of the places now has bromine. Okay. We'll end up getting HBr. That's going to be the overall. Remember, for this free radical chain mechanism, it actually took place in 3 steps. You do need to know these 3 steps here. They are the initiation step. They're the starting step. Remember, it's the initiation step that actually requires the UV light. We need the high energy source to break apart the halogen. Right now, bromine, right, it's just minding its own business here. In the presence of UV, you can actually just pulse UV light. It doesn't need to even be a constant stream of UV light. But UV can actually cause homolytic fission. It can break up one bond into 2 even electrons. And therefore, remember when we draw our arrows, Usually you don't draw arrows like, oh, the bromine goes this way or whatever. Usually your arrows refer to actually electrons. So in this case, my electrons, I had 2 electrons because so far we've only been dealing 1 electron moving. So we just use a fishhook. This 1 electron goes back to one side, the other electron ends up going back to the other side. And then I have 2 bromide radicals. Each of them have an unpaired electron. Notice they're uncharged. They still had 6 outer electrons anyways. It's that bromide radical that I need to begin with. Then I can follow up with my propagation step. Propagation just means sort of carry through, sort of the ongoing. We saw that it was a chain lastly. So I have my bromine radical here. I have my ethane. I'm just going to draw one of the hydrogens just for clarity here. Bromine, in the presence of this ethane molecule here, bromine can actually substitute its way into this molecule. And here's how this happens here. We're going to end up getting the hydrogen. 1 electron is going to end up joining with this 1 electron here. We're going to end up getting HBr and then forming an ethyl radical, and then we'll see what happens afterwards. So let's do that there. So we end up having HBr. Right. So a substituted bromine compound, and we've ended up forming a ethyl radical. And it's actually this ethyl radical. I'm going to draw it backwards here. CH3, CH2 with a dot. It can react with another, it could be just another bromine radical, but I'm guessing there are not a lot of them. It can actually react with another just bromine halogen. And what ends up happening is this 1 electron, again, still the fishhook, bonds with one of the electrons there. And that's basically to substitute on the bromine. And therefore, I would then have a CH3, CH2 with a Br. And then I've regenerated my bromine radical. That's why it's a chain. Now the bromine is ready to attack again. If it attacks again on the same molecule, I can end up getting a very highly substituted, maybe 2 bromines on this carbon and 3 bromines on this carbon. It can happen again and again. Okay, so that's the propagation step. In terms of a termination, in terms of when this reaction might end, it doesn't continue on forever. The termination step here is actually going to be, well, sometimes a bromine does end up running into another bromine. It doesn't really have a preference who to run into. It's just a random chance of who collides with good energy, good geometry. This ends up reforming my bromine diatomic. I can end up having just a bromine radical run to one of these ethyl radicals. So that would end up forming my compound. So ethyl radical here, CH2, CH3. And that's just going to join together, CH2, CH3, and then now it has a bromine attachment. It's a bromoethane. Or for a very trace amount here, we're not going to produce a lot of ethyl radical anyways, but if I happen to have 2 ethyl radicals very lucky in actually colliding with each other, I end up forming a butane. Again, not the best way of forming a longer chain. We're going to do a process called reverse cracking in the energy option, but this one here, we only get trace amounts. And that's only because we're not going to get a lot of ethyl radical, and even if I produce ethyl radical, it probably run to other bromines or bromide radicals to do the substitution reaction. Okay. So far those are the 2 types of reactions here. Today we're going to introduce, this is alkene here is a family. It's a nice precursor to a whole bunch of other families here, because this one here is a nice starting part. We're going to identify the reacting portion of this, and we're going to see how this builds to our mind map. So what do you know about an alkene? An alkene here, the general formula would have been CnH2n plus 2, but because we formed a double bond, every time you form a double bond, you actually lose 2 hydrogens. Alkenes with 1 double bond generally have the formula CnH2n. Being a double bond, you actually don't just want to say double bond, you want to say double bond between carbons. We know that one of these is actually a sigma bond, and one of these is actually a pi bond. So for these carbons that are making up that bond there, we know it's actually C. The sigma bond is along the internuclear axis, so that's the stronger one. That's the one that allows for free rotation. Were it not for the pi bond were parallel p orbitals that just happen to be close enough together. If you were to actually twist this double bond, you would actually need to break the double bond, which is why having 2 bonds here ends up actually not twisting. It's fairly rigid. Okay. So let's just make a comparison here. Alkanes with the formula CnH2n plus 2, they only contain single bonds. They're fully saturated. They contain the maximum substituents, the maximum things attached to it. So they have the maximum number of hydrogens or whatever else has sort of put onto it. The alkenes we're going to look at only will have, every time you form a double bond, you lose two. We're going to assume just having one double bond. And again, it's not enough just to say double bond. You need to say it's a double bond between carbons. And these ones here are unsaturated. These ones here will not only produce a part of the molecule that's rigid, that doesn't twist. If we start thinking about fatty acids usually have a glycerol and then have a alkane chain here. They're all really parallel here. An unsaturated fat would basically take this chain here. If I happen to have, let's say, a double bond here, and I happen to have the cis isomer, then the rest of this chain will actually get kinked off like this, and therefore the chain would actually be a little bit easier for our bodies to metabolize here. That would then be referred to as a unsaturated fat. So as you increase unsaturation, as you increase double bonds and triple bonds here, you're making the molecule not stack together as well. You're making it less viscous. You're making it easier to break down. Okay. Note the bond enthalpy for a C double bond C is 612. For a C single bond is 348. Why is this one here not exactly double? Although a double bond is stronger than just having one single bond, the double bond is not twice as strong because a double bond contains a sigma and a pi, whereas a single bond is just a sigma bond. The sigma bond here is actually more attractive because it's purposeful overlap, whereas the pi bond, it just lucked out sort of side by side to actually react. So why is this important for an alkene? Why does it actually make it reactive? Therefore, it's actually energetically favorable to convert your alkene, which has a pi bond, right? The weaker the two bonds, we want to convert it back to a sigma bond, right? Yes, having two bonds is stronger than one, but let's have two single bonds rather than one sigma and one pi bond. Just a connection to our kinetics section here, the EA, the activation barrier. The activation barrier for this process is low due to a very electron-rich environment, due to a high electron density in the pi. Right? So I just want to use this opportunity to actually introduce you to two main names that we're going to see. We're going to refer to an alkene because it has 4 electrons. It's a very electron-rich portion. We're going to refer to this part here as actually a nucleophile. So a nucleophile, let's take apart that name here. Phileo means liking. This is liking of a nucleus. A nucleophile here is an electron-rich region that seeks out or attacks nuclei. It seeks out positive places because it likes the nucleus. We can have what's referred to as an electrophile. This time it's actually the electrophile that's going to be added to the alkene. That's why it's called electrophilic addition. An electrophile is the opposite. Phileo again means liking. These are liking of electrons. Now I know electrons actually have negative charge. That means an electrophile is actually an electron deficient or an electron poor region. I don't have a lot of negative density right now. Electron deficient region that seeks out or that attacks electrons. That seeks out places that are negative. Okay, so alkenes, based on these sort of properties here, well, the pi bond is actually weaker, it's energetically favorable, the activation barrier is actually low. Alkenes are way more reactive than alkenes. So what we're going to do is I'm going to show you, just sort of in summary, these are some of the reactions that we can actually add to the alkene. We'll talk about the mechanism of how it happens on the next page over. Some simple reactions of alkenes are shown below. It's important that you know these names here. This is called electrophilic addition reaction. We're going to have something referred to as an electrophile. In this case here, it could be the hydrogen here. This one here as an electrophile, as I mentioned, an electrophile seeks out places that are negative. This electrophile is going to add itself to the alkene. Because the alkene was a nucleophile, the alkene was actually very electron rich. Now, as a general rule, it'll always be positive seeks out negative, negative seeks out positive. But depending on what's actually being added here, we're going to have sort of our alkene as our foundation, and we're adding our electrophile to it, and that's why it's called electrophilic addition. Okay? It's going to interconvert our double bond into a single bond, allowing for more of that free rotation. So here's just a few names for us to know here. We can hydrogenate something. Careful the name here. This is not hydration. Hydration will come a little bit later. Hydrogenating something here involves adding hydrogen to something. So here's what happens. we have an HH. This is a diatomic. This doesn't need UV light. This will actually happen. This one actually needs to be a little bit hotter. So usually we quote 150 degrees or so. We're actually going to use a catalyst. We'll see how this behaves later on. Eventually, the overall process is this alkene is like a spaceship, and it's going to pick up the hydrogen. So here's what ends up happening. We actually have, just sort of hinting at what's going to happen here. We're going to have our nickel catalyst. Our nickel is actually going to be a solid. This is a heterogeneous catalyst because the rest of them are gaseous. We're going to have a hydrogen. It was just minding its own business here. Hydrogen was diatomic. It was a gas. What nickel is going to do is it's actually going to temporarily break apart the hydrogen-hydrogen bond. It's going to form two hydrogen radicals. And what's going to happen then is this alkene, like I mentioned, like a spaceship, it comes over top of this one here. Remember, an alkene is actually sp2, sp2. It's actually trigonal planar on both. It's flat. And what it can do is it can actually pick up both of these hydrogens and end up forming, let's see if I can color code it for you here. We have C. We still have the alkene having the 4 attachments as it did before, and now it's ended up picking up 2 extra hydrogens. Okay? So I have hydrogenated this thing here. We've converted a double bond to a single bond here. By adding this hydrogen here, this is actually causing the thing to become more saturated. Okay? So hydrogenation here, again, we're going to go over the mechanism on the next page over, but that's what ends up happening. You end up adding the hydrogen. I want to be careful as you're doing arrows. Yes, earlier I was saying, oh yeah, the hydrogen gets added this way. Usually in organic chemistry, when we're talking about arrows, we're talking about what the electrons are doing. And when we see the mechanism, the electrons actually go in the opposite way. So just be careful. Yes, the hydrogens get added to it, but when you're drawing arrows, it has to be referring to the electrons. Okay. So I've added a hydrogen across the double bond. I've converted to a single bond. Similar things are going to happen as I add other things. I can add a hydrogen halide. A hydrogen halide here is going to be an HX, where X is just going to be a halogen, okay? Where X can be fluoro, chloro, bromo, iodo, right? Exactly the same thing. Well, let's just make a prediction. Well, we've seen because the electrophile added itself across the double bond, this one doesn't need a catalyst. So usually we just say RT. RT just stands for room temperature. But essentially the same thing, the carbon would end up converting its double bond to a single bond, and now what we've done is we've ended up adding the HCl across that double bond portion, right? So we ended up forming a chloroethane. Okay, I've just picked up the hydrogen halide. Or better yet, let's attack a halogen directly, diatomic. So let's say a BR-BR. Any predictions for what I get? Well, again, what's going to happen is this one here as my electrophile is going to be added across the double bond. We're going to have our alkene, so alkene has become an alkane, and now we've ended up picking up a bromine-bromine. This one here also takes place at room temperature, so no other special conditions are needed. What's really nice about this one, this is a nice test for alkane versus alkene. This one here takes place at room temperature. It doesn't need any other treatment. This one is going to take a sort of reddish, brownish liquid. When the bromine ends up adding to it, this one here is actually going to be colorless. So I alluded to this last day here. Let's take 2 beakers. Let's say this one here has an ethane, so CH3, CH3, so an alkane. This one here, let's say, has CH2, CH2. Let's put this brown Br2 liquid into both of these. Okay. Now, we just did in our warm-up question here, yes, an alkane can also substitute, nucleophilic substitution here with the Br2. Sorry, free radical substitution. And this one here would only occur, this only occurs with the presence of UV light. We needed UV to initiate the reaction to create the first radicals that you need. Whereas in this case here, the bromine just naturally adds to it. If this reddish brown liquid, when you add it to it, if it's already reacting room temperature, that's an indication that this one here is actually the alkene, because the other one actually needs to be in the presence of UV light. You can verify that, pulse a little bit of UV light in there, and then that reaction would actually occur. The bromine color would actually slowly disappear. So the fact that alkenes react with bromine with room temperature, it's a very simple lab test for the presence of having multiple bonds. You can even have a triple bond. You can even have many different double bonds here. If the bromine just adds across the double bond, it's going to end up informing you that there's a multiple bond. So we're going to add, typically we're going to add bromine solution. It could be just pure bromine, but usually we've diluted it in a little bit of water, make it less concentrated. Add bromine solution to your compound. If we have either a C double bond C or even a C triple bond C, so an alkyne would do this reaction as well. If these are present in any form, the brown color of the bromine, the brown color disappears. Right? It's going to become colorless. So far we're starting to see a more interesting reaction here. Alkenes, because of this double bond, because of this electron-rich area, it's actually able to add a bunch of these compounds. I can add hydrogen, I can add hydrogen halides, just the halogen itself. We'll end off with this one here with hydration. Hydration here is actually the addition of water. So yeah, I want to add water across here. In this case, I want you to think of water here. I know it's a covalent compound, but it's sort of like an HOH. It's also like, if you just compare it here, it was H bonded with something, it could be H with the halogen, just the halogen itself. This is H with the hydroxide. You can make a prediction. Note here, this one here is actually an equilibrium arrow. This one here actually requires concentrated sulfuric acid to actually catalyze. Right? So as a temporary precursor here, the catalyst enters the reaction. It's actually the H2SO4 that actually adds across the double bond first. So we're going to end up having, this is your alkene. It's become an alkane. We're going to have our sulfuric acid. One of the H's are on one side. The other side is going to be the rest of the sulfuric acid. And then for this one here, as you add water, as you have your hydration, right? Water is your chemical that you're ending up adding. Water ends up taking the place of this one here and ends up, what we would have expected earlier was we would still have the H. Actually, that H here was actually sulfuric acid's H, but what ends up happening here is we end up getting an OH, and the water ends up giving the H back to sulfuric acid here. And again, we're seeing this generalization. We're adding something across the double bond here. It's an addition because we're taking two things, almost like a synthesis, and end up becoming one thing. Right? So what I want to show you on the next page over is what's the mechanism of this look like? How come alkenes are so reactive? You do need to know this mechanism in detail. So let's just flip over to the back. In order to understand why these reactions are called electrophilic, so this is a electron deficient region that ends up seeking out a negative. So this is an electron poor region seeking out a negative density. In this case here, it's going to be the density of the multiple bond, the single bond with the pi bond there. And then we're going to add this across the double bond. We need to look at the mechanism. So this is the halogenation that we said from earlier. We're going to add a straight diatomic halogen across the double bond. Here's the details. Here's the mechanism. And after we learn this mechanism here, you can actually go back and look at, well, what would be different if it was a hydrogen or a water or whatnot. Okay. So here's what's going to happen. We are eventually going to add this one. This one here is called the electrophile. The electrophile is going to be added across the double bond, so it's called electrophilic addition. But it turns out who is going to attack the electrophile is actually this double bond, right? So this is what happens. I know bromine and bromine here is nonpolar, right? I know it's actually, there's no polarity to it. But because electrons constantly swish and swash, I can temporarily have the electrons switch to the right-hand side. I've created a temporary dipole, a temporary negative on that side, a temporary positive on this side here. Okay. A second later, the electrons would have swashed the other way, and now the dipole is going the opposite way. Because there is a polarity involved, because there's a relatively positive region, again, when we draw arrows, careful, we actually want to focus on what the electrons are doing. I'm going to take the two electrons involved in the pi bond, and these two electrons are actually going to attack the positive side of the bromine here. This time you'll notice it's a double-headed arrow because it's actually both electrons that actually attack the bromine. So what ends up happening? So we're going to temporarily, this is sort of a mid-step here. I had temporarily taken the two electrons here involved in the double bond. I then sort of, almost like a dative bond, I've then attacked just the one bromine side. Okay, I've actually pulled this bromine. As that happens, the bromine here, which actually has a bond in between, there's two electrons there, these two electrons are scared of these electrons that are coming in, and those two electrons also jump back onto bromine. So what we're going to end up having, I'm going to end up having grabbed one of the bromines, and now we have our bromine as actually a negative charge. if you just sort of look at sort of conservation of charge here, because I've ended up grabbing a Br, just the positive part of it, not with its extra electron, now this guy here has actually become charged. If you do your 4 more charges, we've actually created a carbon that's actually positive. That part there is referred to as a carbocation. Right? Carbon, that's actually a cation. And then as a second step, what's going to happen? Well, if one's negative and one's positive, this carbocation here can end up attacking the carbon. It's going to then attach to the other side. It just turns out if you look at your hybridization, this carbocation here, so I'm going to give you the name here, the carbocation, the carbon that's positive, carbocation is sp2 hybridized. And if you can think back to your grade 11 stuff here, sp2 hybridized meaning it's actually trigonoplanar. This part here is actually flat, meaning your bromide, this bromide ion that got kicked off, right? The just so happened to be the negative end here. This bromide can actually attack from the bottom or attack from the top here. So based on that, you might say then, well, then I can have a compound. Well, so that's sort of the mid step here. One compound could be, based on the way I drew it, CH, I've grabbed onto the Br, that's going to look like any old covalent bond just like before. And then let's say the bromine has actually attacked from the top. So therefore, I'm going to have carbon. Its hydrogens here are going to be on the bottom, and then I'm going to have Br like this. Or it could be another reaction here where, let's say the bromine attacked from the bottom, and I have a CCH like this, and I end up having the Brs. Notice I've done it. I've added the electrophile to my alkene, so electrophilic addition. Are these isomers of each other? Well, in this case here was a little bit redundant. Wait a second. This one here is actually a single bond. This single bond allows for free rotation. Right? It is just a sigma bond here. There's no pi bonds that are actually breaking. So these two are actually identical. They are not isomers. So you just need to draw one of them. If you want the bromine on the bottom, you just rotate it around, and that part there will just be a different conformer. This is identical to the one on the top. Later on, when we start taking a look at other organic reactions, depending on which side that we actually attack from, if the geometry matters, we might get our R, or if it attacks from this side, it might get our S isomer. We actually will end up getting isomers. But so far, no problem. This one here is actually identical. This is not an isomer. How do chemists know that this is the mechanism by which it takes place? So far, we've added the bromine across. I don't know which bromine was the partial positive or partial negative. I see that both bromines get added. What we can actually do here is actually experimentally, I can actually add in different halogens. So let's say as I do this reaction by adding Br2, what you can do is you can actually add, very simple, also at room temperature, let's just add NaCl. Well, where did the NaCl come from? It doesn't really matter. The NaCl is just a soluble compound. It's just going to provide extra chloride ions. So let's think about this mechanism again. We had a C double bond C, right? This one here was flat to begin with. It first attacked our bromine neighbor, right? So we're drawing arrows to show what the electrons are doing. The double bond here is going to seek out places that are partially positive. These electrons are going to go back on the bromide. That's going to be Br dot dot. Therefore, temporarily, we're going to have created CC like this. We're going to have grabbed a Br. We've ended up forming our carbocation again. It's a carbon that temporarily has a positive. Now, earlier when it was just bromine in solution, it's only bromide ions that add. This time, when we actually test for it, yes, sure, there are still bromide ions. Yes, sure, there's going to be a lot of them that actually end up having two bromines across that double bond there. But because I also have Cl minus, Cl minus can also add itself. Well, it is a positive charge. I can attack on top or below. And based on the existence, when I actually test for the compound, because I end up finding some sort of asymmetric compounds here, I have a Br attached to one and a Cl attached to the other, I realize that this is the mechanism. Not necessarily taking place in two steps. This could all be happening all in one succession, but at least this happens first and then another thing happens. Couple other side notes as we just finish off here. In the example above, the electrophile Br2 is symmetrical. You can't tell one Br from the other Br. What if we used an asymmetrical electrophile here? We had already added an alkyl halide, a hydrogen halide from previous. This one here was asymmetric. We saw the hydrogen add to one side, the halide add to the other. Now we know the mechanism, we can actually make some predictions. So Again, arrows for the arrows for the electrons. This is going to be a double hit arrow because both electrons add. This time we're not relying on the temporary dipole. This time hydrogen bromide is actually a polar compound. It will always have the hydrogen side kind of positive, the bromine side kind of negative. So when we have the electrons in the double bond, they grab the hydrogen. So we end up getting CH like that. We end up grabbing almost like a data bond here to the hydrogen here. Right? It forms a covalent bond. The bromide temporarily holds on to the electron, and the bromide can, as a second step here, can come back and attack the carbocation. Can either attack above or below, and again, didn't actually change isomers because this bond here is actually a single bond. So therefore, we've added our alkyl halide across, and now we end up having our hydrogen, bromide, asymmetrical, added across the double bond. The double bond has converted itself to a single bond. Okay. So here are some sample questions here. Let's draw the mechanism for the electrophilic addition of HCl to butene. They've already drawn butene for you. You should be able to identify for me. This one here is actually the cis form, or the E isomer. Right? Sorry, the Z isomer. Z is same side. Same thing happens. So let's just add this double bond. Let's take this double bond here. Let's attack the partial positive side. It's always the hydrogen side, the partial negative. We're going to end up getting, this time our alkene is a little more complicated. Our alkene actually has two methyl groups here. The double bond has now become a single bond. So single bond like that. It still has the butane sort of structure. We have H and H. I temporarily grab that hydrogen. I have a carbocation that ends up forming, and the question then is, well, the chloride is then going to add, being a negative. I'm tracking the electrons. It's actually going to add to the carbon side. So again, you can make a prediction fairly easily. Overall, in all these examples, it's just having added the electrophile across the double bond, converting the double bond to a single bond. Now, there's one last interesting note we're going to finish off with for this section here. What if the alkene is asymmetrical, in this case here, like propene? So propene, unlike, well, it's very even. The carbon has a methyl group on both sides. This one here, one has a methyl group, the other side has a hydrogen. Now what's going to happen here is, okay, we have our propene, right? You could have said one propene, but it's actually the only place we can do it. Chemists are lazy. They just drop that one there. And let's try to do the same thing. So HCl here is a polar compound, is a positive end, and has a negative end here. We're going to take our double bond. We draw arrows for the electrons. The electrons are going to attack the hydrogen. These electrons go back on the chlorine. So we're going to end up getting two possibilities. Either we're going to have, well, as I've drawn it, maybe the hydrogen ends up adding to the left side. And then we have our methyl group, the rest of our propene, H, and I have a carbocation. Or it's possible I have, because it's asymmetric, you'll actually be able to see the difference. What if I had the hydrogen actually add to the other side? In both cases, you will form a carbocation, right? That's fine, no problem. But it actually is going to be important now because we're actually asymmetric. Now that we have a chloride, chloride is just going to add to the carbocation. If the chloride adds to this carbocation, we're going to end up getting CH. So I'm going to have a chlorine and I have a hydrogen. But being asymmetric, or the chloride actually adds to this carbocation and it ends up creating H3H. We're going to have H. Are these identical? Okay. Well, let's take a look at the name of them. This one here would be a propane, right? All single bonded. It has a chlorine on number 2, so this is actually 2-chloropropane. Versus this other one here, if the hydrogen chloride actually added the other way across the double bond, it adds to one of the carbons no matter what. But this one here is actually 1-chloropropane. Notice it has a totally different name, so it's definitely not identical. What's the relationship between these two? Hopefully you're able to say to me here, the relationship for these two here, they are structural isomers of each other. They are, imagine taking the chlorine and just reattaching it on another part here, totally different physical properties. What we want to do here is, if we can, sometimes it's impossible, it turns out that one of these two products is formed more readily than the other. Although both of them are possibilities, one is more likely than the other. So let me just re-sketch it for you here. Let's look at the two possible mechanisms. I already started sketching it out for you. Again, the double bond attacks the hydrogen. The hydrogen is going to attack one of the carbons. So we're going to have, let's say on the one side, hydrogen attaches to the left. I get a carbocation like this. Or I have the hydrogen attached to the other side. It's the same attack, but this time, sorry, the hydrogen is actually on this side here. We have a carbocation end up forming, and the hydrogen attached to the other side. Because it's asymmetric, this time I'll know the difference. The reason why experimentally one forms much more readily, you might end up getting both, but usually we refer to one as a major product, one is much more common than the other one. It actually has to do with this middle step here. Carbocations in general are unstable. So if I can argue for the stability of a carbocation, that's actually going to predict, would this one here be more stable or would this one here be more stable? And what we're going to actually do is the stability of a carbocation actually depends on how many alkyl groups, how many other carbon groups are actually attached to it. This is something called the positive inductive effect. It's a helping inductive effect. Alkyl groups, which are carbon groupings, these ones here can actually donate electrons to help to stabilize a carbocation. So here they've sketched for you 3 carbocations. The carbocation, this positive carbon shouldn't be stable. This so far here is a primary carbocation, because it has one other carbon neighbor. Because there's an alkyl group, although this bond here is going to be 2 electrons, the carbon can actually donate some of its electron density. It doesn't actually physically give its electron and actually break off, but it actually donate some electron density. So donate electron density to stabilize the positive charge. Again, overall, it's neutral. It can't get rid of the positive, but it can help to spread out that positive charge. In fact, the more carbons that I have, now we have a secondary carbocation. Now I have 2 alkyl groups doing it, or I have 3 alkyl groups doing it here. Based on our carbocation stability, we actually have increasing stability as we go from primary to secondary to tertiary. So, increasing stability. So, in fact, as we look at these 2 possibilities, is there a situation where, well, this one here, this one is a secondary carbocation. It has 2 alkyl groups here trying to stabilize that positive, whereas if I have the positive on the other one here, this one only has 1. Because a secondary carbocation is more stable, so more stable with 2 groups. So 2 groups inductive effect. Because this is more stable, this one here is going to be more likely. So when the chloride ends up adding, the chloride is going to add to this position here. Again, notice where I've drawn the arrows here. It's from the electrons. And therefore, we can say between these 2 products, although the other one is possible, I would expect the major product to be the one that went through this mechanism, the one that actually had the more stable carbocation. And that's referred to as the major product. Okay. It had the mechanism with the more stable of the grouping. And all you need to do is exactly that. When you actually look at the carbocation, you want to see how many alkyl groups it's referred to. All of this reasoning here can be summed up in something called Markovnikov's rule. Okay, Markovnikov is just a nice shortcut. If we're not actually drawing out all this, all the carbocations, all the possibilities, and then checking primary, secondary, tertiary, whatever, Markovnikov says if you add an asymmetric halide, so hydrogen halide, this one here can be fluoro, chloro, bromo, iodo. If you add it to an asymmetric alkene, the hydrogen is actually going to attach to the one that already has more hydrogens. So usually this is shorthanded, he who has gets more. Okay? That's usually, I think that's unfair. You already have more. Why do you get more? Well, if you look at it here, we have 1 carbon that has 2 hydrogens, 1 carbon that only has 1 hydrogen. If I add an asymmetric hydrocarbon across it, you notice my major product, the one that already had 2 hydrogens is the one that's actually going to gain an extra hydrogen. The other part is going to add across the other side. That was our major product. The reason for that here is if the hydrogen adds to the side that has more hydrogens, you'll notice the other side would have been the more stable carbocation. Right? The other side would have had carbon more highly substituted, and therefore the carbocation is much more stable, and therefore we would add it in that fashion. So Markovnikov's rule, it's just a nice hint for you to predict which side the hydrogen adds to. Okay, I'm going to add this to our mind map tomorrow, but it's a good idea to just practice drawing on the mind map each day. Okay, let me know if you have any questions. Thanks, guys.